Okay, so Coralie is going to tell us what finds in entropy and quantity, and this project is supervised by Dr. Elliott-Wogan. So Coralie, please go on.
Hi everyone, welcome to the presentation on the Maximum Entropy and Quantum Gravity project. My name is Coralie Elliott-Wogan, and I'm in my third year of undergraduate study of theoretical physics at Trinity College Dublin. Today I'm going to share with you what I've been doing over the past 8 weeks. So starting with an introductory section where I just give you a little bit of background in black hole thermodynamics and the idea of gravity imposing a minimum uncertainty in length. I'll then move on to talking about T. Hough's brick wall model and how it can be used to compute the entropy of a black hole. I will then apply the idea of the minimum uncertainty in length to the computation of entropy from the brick wall model. T. Hough's brick wall model for computing the entropy of a black hole has been shown to have significant divergences in the entropy and a strong back reaction effect from its test field. Don't worry too much about what that means yet, I will definitely explain in due course. But what I've done is apply the gravity modified computation to this model to see if it has any impact on these results. And what I found is that it does not fix the problem, but rather enhances the original results. The conventions used are natural, where h bar is c, g is the Boltzmann constant, everything is just equal to 1. Sometimes I will state the Planck length explicitly because it's needed to distinguish modified terms from non-modified terms, and this is the metric signature being used. So what is a black hole? A black hole is a region in space-time where the gravity is so strong that beyond a certain threshold, not even light can escape it. This threshold is called the horizon. I've created a timeline of discoveries in black hole thermodynamics, which will hopefully give an intuitive picture. In 1972, Bekenstein notes that the black holes have a classic area increase law, which makes them a good candidate for the entropy. In 73, Bardeen, Carter, and Hawking note that the first law of black hole mechanics is analogous to the first law of thermodynamics. In 75, Hawking publishes his iconic paper, Particle Creation by Black Holes, where he identifies the relationship between entropy and area. And then in 1981, Bekenstein proposes a universal bound on the entropy of matter to explain some apparent paradoxes associated with the generalized second law. The discovery that black hole mechanics might just be extensions of the laws of thermodynamics hints at a fundamental relationship between gravitation, thermodynamics, and quantum theory. The quasi-static lowering of a box containing matter towards the horizon suggests a slight issue with the generalized second law, because by the time the box reaches the horizon, it will have lost all of its energy when it falls into the black hole. This means that the area of the black hole shouldn't increase, but then the entropy of that system is lost. And it was this alleged paradox that led Bekenstein to propose the universal bound on entropy. So we can see that in the case for a short-term black hole, this is actually just the Hawking entropy, which is interesting. It tells us that a black hole is a maximally entropic system. Also, the absence of G from Bekenstein's bound tells us this is actually a QFT result, not a quantum gravity one. So the addition of gravity to quantum mechanics implies minimum resolvable length. And this can be visualized by imagining shining a light on a small length to resolve its distance. The smaller the distance, the more photons need to be concentrated in a single area in space in order to be able to resolve this distance. And if you want to resolve an infinitely small length, we would need to have an infinite density of photons at a particular point, which breaks down in general relativity, so there has to be some kind of minimum length that's implied. And this happens mathematically with the modified uncertainty principle. So you can see that now if we take the limit where delta p goes to 0, delta x doesn't go to infinity anymore. So we have this minimum length. Just in terms of notation, I'll generally refer to alpha as alpha naught times the Planck length squared, where alpha naught is just dimensionless, and this just means that everything is appropriately unitless. And then this is the gravity modified commutation that is implied by the modified uncertainty relation. then the computation of Hawking entropy, taking this modified computation into account, is relatively straightforward, so I will omit it just in the interest of time. What we see is that area is proportional to the mass squared. So the first term is proportional to area, and the second term is a logarithmic correction. This logarithmic correction is well established in quantum gravity and follows from any particular quantum gravity approach. So when we compute the entropy from T. Hooke's brick wall model, we should expect to see something of a similar form. I thought I would also just show you a cute little diagram which is called the Bronstein limit cube. This just visualizes the different branches of physics based on which fundamental constants are important. We're, of course, in the quantum gravity corner, where G and H bar and 1 over C are all significant. If you take the limit as H bar goes to 0, you find yourself in general relativity, and if you take the limit as G goes to 0, you find yourself in quantum field theory. T. Hooke's brick wall model is actually originally a QFT model, so when we bring in this modified commutator into the picture, we're trying to generalize up into the quantum gravity corner. If H bar is just important to your quantum mechanics, if G is important to your Newtonian gravity, and 1 over C special relativity. Hopefully, you can also see that the addition of the Planck length squared term to the commutator brings us from quantum mechanics into quantum gravity, since the Planck length depends on G, C, and H bar. But anyway, on to the actual project now. Okay, so I will just attempt to explain what T. Hooke's brick wall model is. The setup is a black hole with a scalar field outside of it. We compute the Boltzmann entropy of this scalar field, and we expect that it should in some way correspond to the entropy of the black hole due to the quantum entanglement between small vacuum fluctuations just outside and just inside the horizon. We have an infinite blue shift for an observer sitting just at the horizon of the black hole because of the massive acceleration required to prevent oneself from falling into the black hole. And because of this, the entropy appears infinite. This is obviously problematic, so we include an ultraviolet cutoff at a small distance, epsilon squared over 2m away from the horizon. This distance isn't arbitrary, it's just based on geodesic distances in Schwarzschild spacetime. Nothing too crazy. So we then solve the Klein equation for the wave function of the scalar field, and then the exponent of the wave function is the wave number, which is intrinsically related to the number of particles. Once we have the number of particles, we can compute the partition function, and from there, any other thermodynamic quantities that we might be interested in. You might be wondering what particularly is physical about the cutoff at r epsilon. Definitely, initially I thought it was slightly strange, but actually we've established that epsilon is small, similar in order to the Planck length, and the generalized uncertainty principle tells us that there exists a minimum resolvable length to the order of the Planck length as well. So actually, the closest we can get to the black hole, while also being certain that we are indeed above the horizon, coincides with this distance r epsilon. So it does actually make sense to do this. In this project, I've been dealing with Schwarzschild black holes, so we use the Schwarzschild metric. This modifies the D'Alembert operator in the Planck coordinate equation to this particularly lengthy expression shown, but hopefully the last term is familiar to people as the operator that yields spherical harmonics as a solution. So we can write the ansatz for the wave function as separable since the black hole is static and spherically symmetric. We naturally get angular harmonics for the angular solution and an exponential in time and energy for the temporal solution. This leaves us with a simple differential equation to solve for the radial solution, which we do using a WKB approximation, which is acceptable because we're working in the semi-classical limit, and the classically forbidden region is emitted by the ultraviolet cutoff that we used before. This is the solution that we get, where k is the wave number corresponding to a specific azimuth quantum number. And you might notice that the integral has an upper limit which is not infinity. This is just because if it was, we would have an infinite number of particles if we were considering all space. So we also have to include this infrared cutoff, which is yet to be defined. We sum over all quantum numbers to get a more general expression for the wave number, and we make a few approximations since we're in the semi-classical approximation, which is a high frequency limit. We then define the infrared cutoff as the zero of this function, because if r was larger, then k would be imaginary, which is not great. So then we get the number of particles. Since epsilon is small, we expand in powers of the small distance epsilon squared over 2m from the horizon. This means we can discard any non-divergent terms. So these are terms not proportional to 1 over epsilon to the power of something, or terms not proportional to the logarithm of epsilon. This is what we get for the number of particles. And we're then able to compute the partition function and the thermodynamic quantities that we want. Full derivations of the expressions I used on this slide are outlined in my report. Anyone that isn't convinced, which would be totally fair. Okay, so let's just talk now a bit about what we should expect from our thermodynamic analysis. We've constructed a probe field, so we expect to have a negligible back reaction effect. In the simplest terms I can manage, this basically means that the energy momentum tensor is too small to alter the background metric. We sort of have this semi-inequality here, which is not really an inequality because they're tensors, but you get the gist. We'll often take the limit where the mass of the scalar field goes to 0, because we want our results to be independent of the dynamics of the field. And based on the modified Hawking entropy, we expect to have some terms proportional to the area and some logarithmic corrections. So let's see what we get. Starting with the free energy, while the sign is dependent on the mass of the scalar field, in the limit of the mass of the scalar field, it is decidedly negative. So this makes sense, since the scalar field doesn't work on the black hole, energy tends to flow into it. The entropy is exactly what we expected, with one term proportional to the area and one logarithmic correction. The logarithmic correction is significantly larger than it was for Hawking entropy. Before it was proportional to Planck squared, now it's just not. So maybe a little bit concerning, but nonetheless, it's a good candidate for entropy so far. The internal energy is where things start to go a bit awry. It's a significant fraction of the mass of the black hole. This means that the energy density is large, and from the Einstein equation, that means the radial component of the metric will be significantly altered. So we have a strong back reaction effect. This is definitely not what we want from our probe field. And furthermore, the heat capacity is positive, which is not true for black holes, so this must correspond to the stable exterior scalar field. So just to review, the entropy looks promising from the outset, but the internal energy indicates a strong back reaction effect, and the heat capacity is positive and so corresponds to the external scalar field. The rest of the presentation will now be dedicated to applying the modified uncertainty principle to this model to see if it has any appreciable influence over the results, which I think is a natural thing to expect, since we've gone this small distance away from the black hole, which is in some way related to this minimum uncertainty in length. Just to review, this is the commutator that we'll be using. We solved the Klein-Gordon equation for the wave number to get the number of particles, the partition function, and then thermodynamic quantities. It's worth noting the equivalence of the Klein-Gordon equation and the energy momentum dispersion relation. We use this fact to get the modified expression for the Klein-Gordon equation. We use various properties of the commutator to get a differential equation for the momentum as a function of the wave number. And we substitute this into the energy momentum dispersion to get this modified Klein-Gordon equation. So whereas before we had a 0 on the right-hand side, we now have this extra term. This is what we need to solve to get the wave function, which is considerably more complicated, but luckily for you guys, I've already done it, so I'll just tell you what the results are. Just to remind you, we want to have a negligible back reaction from the scalar field. And then we want to have, particularly in the limit, as the mass of the scalar field goes to 0. Just in terms of notation, I use the subscript O or IG to indicate a thermodynamic quantity before the addition of the modified commutator. And just a warning that the expressions on the next few slides are quite long, but I've done my best to sort of condense them into more manageable chunks, so hopefully that's okay. The full expression for the free energy contains the original expression and modified terms proportional to 1 over epsilon squared, 1 over epsilon squared, and the logarithm of epsilon. I've removed some of the clutter by defining smooth and finite functions at 1, 2, and 3. These, it also contains 2 divergent pieces, which I've denoted gamma 0. here. These are particularly problematic, but thankfully when we take the mass of the scalar field to 0, these completely disappear. So it's not too much of a worry. Then in the limit of the mass of scalar field, the free energy is still negative, indicating that the field does work on the black hole. Something that's a little bit worrying, and we will see this again and again, is that the supposedly quantum correction adds such a significant modification. The leading order term before was proportional to epsilon squared, and we now have similar order terms, so we're modifying the leading order term, which is definitely not what would be normal for a quantum effect, but we'll see what the other quantities look like. It turns out that the entropy is much the same. We do have some terms proportional to the area and some logarithmic corrections, but again, the leading order term is modified by adding in this quantum correction. In the mass of scalar field limit, the internal energy is still a significant fraction of the black hole's mass, so we haven't fixed the problematic back reaction effect. And the heat capacity remains positive, which means it corresponds to the field and not to the black hole. So we see that in the limit of a massive scalar field, we've removed all of the problematic gamma zero divergences. While the expression for the entropy is in the right form, the significance of the modification is worrying. Both the free energy and the heat capacity correspond to the field and not to the black hole itself. And the internal energy indicates that we have a strong back reaction effect from the field. All of this combined indicates that the quote-unquote probe field that we defined actually has a considerable influence on the dynamics of the system, and furthermore, we can't really consider it a probe field at all. What does this mean for the future of the brick wall model? It's not great. These results demonstrate that there's definitely something going on that we don't fully understand. While we hoped that the addition of the gravity-modified commutator might fix some of these issues, it actually enhances them. One of the papers which I studied for this project calculated the entropy of the black hole using a replicator calculation. So it could be interesting to explore other avenues such as that and adding in the gravity-modified commutator to see how that might influence the results. But anyway, thank you for taking the time to listen to my talk. If you have any questions, I'd be happy to try and answer them. Yes, epsilon is basically the small distance from the black hole. Sort of. It's the small distance is epsilon squared over 2m, but it's basically just a small number to the order of the Planck length.
So you're writing these terms, and you have 1 over epsilon squared and then 1 over epsilon to the 4.
Yes.
1 over epsilon 4 is a bigger term.
Well, it's actually of a similar order because in the numerator, I'll just skip back to the end. So in the numerator, you also have a Planck length squared term. So overall, it's to the same order as 1 over epsilon squared. But yes, it is definitely a worrying result. Yeah.
Can you comment on your modified indicator?
Yeah.
How are you going with that? And how do you look there?
Sorry, just could you repeat that?
The entropy relation is clear.
Yeah.
Maybe now the commutator relation, like what's going on with delta P on the right hand side.
I think that's actually just meant to be P. I think that's a typo. But like they sort of follow from one another. I haven't included a derivation here, but it would be in my full report. I think it's just P squared actually. Yeah, it's just a typo.
And it's an operation.
Yeah. Well, I mean, it's just the momentum squared. Once it's applied to something, it just becomes the momentum squared.
The thing is that the one is essential in the algebra, whereas P is not. So I'm just not sure how we work with that expression.
It's been a while since I've done the derivation. This was something I did at the start. Like, it is possible that I've just written it wrong here, but
If I may, the idea for working with this would be to actually find the canonical momentum that does satisfy, to find some Q such that Qx actually is I and 1. But, that is not a physical moment. So kind of like physical moment would be the commutator is modified, but for practical computation and quantum mechanics, you go from a different momentum, this kind of different place.
So you use, and there's some you are saying that there is P of P hat of P alpha, which is kind of computation.
Yes, they do.
Yeah, okay. Thanks. So
sorry.
you're saying that modified computation will rise to that uncertainty.
It's more the other way around. The uncertainty relation gives rise to the modified commutator.
So, the commutator is the basic one, so you want the other way around.
You could do it both ways. Like, one follows from the other. They're sort of a re-expression of the same statement, but when I did it starting with the uncertainty relation. Any other questions? Yeah.
Do you think that including other quantum effects in your thermodynamic analysis could potentially fix some of the issues with the incapacity?
It's possible. Honestly, I don't, just because this, as far as I'm aware, adding this particular commutator is new. I haven't seen someone else approach it this way, but there's been a lot of research done on this particular model, and it's shown a lot of divergences and issues, so I think it's probably not the way forward. I would imagine we need to look at it from a different perspective, but it is possible, I suppose. Yeah, it'd be interesting to investigate, for sure.
Okay, no more questions. Let's thank everyone.